Hello and welcome to our lesson on finding domain and range. This is going to be from section 2.3 in our text. And what I'm going to do in this lesson is I'm going to jump straight into the examples and explain all of the details and subtleties as we go through the problems. So for our first example here, number 4, it says determine for each one, that means each one of these problems. And then the first thing they want us to find is f of 1. So for part A, f of 1, let me explain exactly what that means. First of all, function notation is f of x, and here we can see that where the x is, there's a 1. So the x in this case is 1, and we should know by now that f of x, all of that together means y. So if you break this down and look at what it's really asking you, it's asking you to find an ordered pair. Okay, so this problem is saying, hey, when x is 1, what's y? And we can do that from this graph. So we need to go to where x is 1, and then we need to go either up or down until we hit the graph, and then see how high or low that is. So if we go to 1 and go till we hit the graph, that's going to be at a height of -2. And so that answer would be -2. So again, these problems, they're giving you an x and they want you to find y. And the y is how high. Okay, it rhymes. And that's it for part A. Now, for part B, it says find the domain. It does not specify whether it wants set notation or interval notation, so I'm going to give you both. So the domain are the values that x can be. And since the x-axis runs left to right, then we're going to be kind of like a flatbed scanner scanning from left to right to see where the graph starts and where it stops. So as we scan from left to right, we can see that this graph starts at -4, and since it is a solid dot, that means we're going to have a bracket and -4. The first notation I'm going to demonstrate here is interval notation, where we have a bracket -4, comma, and then where does the graph stop? Well, it stops at 2. On the x-axis, there is a solid dot, and so that's going to indicate a bracket. So again, do you see domain is from start to finish, and you're picking the x values because the domain are the x's. Part C, all x values such that f of x is 2. Let's break that down. If f of x is 2, what they're really telling you is that y is 2. So again, this is a lot like part A, where I said that they give you the x and they want you to find the y. Part C is backwards, where they give you the y and they want you to find the x. So here we're going to go to where y is 2, and we're going to go either left or right until we hit the graph, and then we're going to see what x that corresponds to. So for this graph, we can say f of x is 2 when x is -2. And that is the only x value where the graph is at a height of 2. Last, we have part D, where they ask us to find the range. So if the domain are the values that x can be, then the range are the values that y can be. So here, instead of going from left to right, like we did for the domain, we're going to go from bottom to top. Like we're like a flatbed scanner, scanning from bottom to top. And we need to know, where does this graph start and where does it stop? So it looks like it starts at -3. That's the lowest that it can be. And then it stops up at 3. That's the highest it can be. And again, since those are solid dots, those are going to be brackets. And it always has to be from bottom to top. Now, like I said a second ago, I said I was going to do the domain and range in set notation and interval notation. So I've got my interval notation. Now let's look at what that would look like in set notation. So the domain would be the set of all x such that x is greater than or equal to -4, but less than or equal to 2. And that is the way we would express the domain in set notation. For the range, it's going to be the set of all y's such that y has to be greater than or equal to -3, but less than or equal to 3. And there is the range in set notation. And you do need to know both of these. You need to know how to write interval notation and set notation. Next, number 8, we're going to go through and do exactly the same 4 pieces that we did for the previous example, but here we have a different graph. So part A, they want us to find, again, f of 1. And again, what that's saying, it says when x is 1, what's y? Well, if I go to where x is 1, and then I go up until I hit the graph, I need to know, how high is that? When x is 1, how high is the y? And that is the answer for that part. Part B, what is the domain? Well, the domain are the values that x can be, and the x-axis goes from -infinity to +infinity. So what we want to know is, really, we want to know, how wide will this graph spread out? Notice the arrow here says that this graph continues to go down, but notice as it goes down, it's also scooting over to the left. So if we let this graph continue to go down to infinity, it will also go to the left and keep scooting over and over and over to the left forever. And so the domain, again, in interval notation, would be from -infinity. And I need to point out that an infinity always gets a parenthesis. From left to right, again, how far to the right will this spread out? Again, if it's going to go down forever, it's also going to continue to scoot over forever. And so this graph will spread out to infinity to the right. And so this particular graph, I don't know if you recognized it, it's a parabola. And a parabola comes from a quadratic function. But in general, a quadratic is a polynomial. So just so you know, any polynomial function is going to have a domain of all real numbers. -infinity to infinity is the domain of any polynomial. This one is specifically quadratic because it's a parabola, And so we know the domain is all real numbers. Now this is interval notation. In set notation, you would say the domain is the set of all x such that x can be an element of the reals. And that is the fancy math notation way to say all real numbers in set notation. Next, part C. We want to find all of the x values where f of x is 2. So what are they actually telling me here? Well, remember f of x means y. So what they're saying is they're saying, hey, when y is 2, what's x? That's what they're asking me. When y is 2, what is x? And so we're going to have to go to where y is 2, and we're going to scan across. Notice that the graph exists at 2 points at a height of 2. And I also notice that if I go down to see where that is on the x-axis, it's in between -1 and -2. So we're going to have to estimate here. So this graph is at a height of 2 at, and I'm going to use the approximate symbol, it's approximately -1 point, I would say 4, because it's not quite at a half, maybe -1.4, and then the other one's going to be at +1.4. And sometimes it's not cut and dry, if you know what I mean. Sometimes it doesn't hit at a nice whole number, and in that case, you just have to estimate, unless they actually give you the polynomial function where you can plug in and solve for x and get that answer exactly. And last but not least, part D, we need the range. And the range are the values that y can be. And the range always goes from low to high. So notice these arrows at the bottom indicate that this parabola will continue to go down forever. So the lowest that this graph is ever going to get to be is -infinity because it goes down forever. And how high does it get? Well, it looks like it maxes out at 4. And since this is a parabola, we're going to say that that vertex, the top point, touches at 4. And so we're going to use a bracket that indicates 4 is included. Now that is the interval notation. We also need to express that in set notation. And so that would be the set of all y such that y is less than or equal to 4. And do you see how that describes the range? This graph, the highest that it can ever be is 4, but it can be anything less than 4. And that's going to do it for number 8. Moving right along, number 23, all they ask for is the domain. So what do you need to know? You need to know that a polynomial function has a domain of all real numbers. Since this is a polynomial, specifically a quadratic, the domain is all real numbers. Now, you can't just write the words all real number. It has to be in a formal mathematical notation. So what would be acceptable? Well, interval notation would be acceptable. We can say -infinity to infinity. That's all real numbers. Or we can use set notation, the set of all x such that x is an element of the reals. Either one of those would be satisfactory. for giving the domain of this function. And I think what I want to do real quick is show you how Desmos can help a little bit here. If you want to check what we can do, and I've got several pulled up that I'm going to look at here. To turn this on, this is our function that we currently have. We can see that it does make a parabola. One of the cool things about Desmos is you can click on the vertex and it will tell you the ordered pair. So if you were doing the range, this would be very helpful. Here, remember the range of the values that y can be. So the lowest that y can be here is 0, and it's going to go up forever. But notice as it goes up, it also gets wider. And so if I go up to infinity, it's going to spread out left and right forever. So this graph will cover all values of x. And that's going to do it for number 23. Next example, number 9. Here they've given us another function, and all they ask for is the domain. So remember, the domain are the values that x can be. This is definitely not polynomial because you have a variable in the denominator. That makes this function rational. A rational function is a fractional function where you have variables in the denominator. And it turns out that rational functions have what we call restrictions. Now, why is that? Well, it's because a fraction bar means to divide. And so this would say 2 divided by some stuff. Is there anything that you cannot divide by? Well, the answer is 0. Division by 0 is undefined. And so what that says, it says this denominator cannot be 0. If it was, you would have an undefined situation. So this is the restriction for this rational function. And then if I solve for x, I'll know what x can't be. Moving the 3 over, here we can see that x cannot be -3. This, written this way, this is not the domain, this is the restriction. If you want to turn this into the domain, you're going to have to turn it into set notation. So we would say the domain is the set of all x such that x cannot be -3. This is the official mathematical way to write the domain in set notation. You could also express this in interval notation if you want to. It's not quite as nice and neat, but it is possible. So what I want you to think of before we go to interval notation is think about what can x be and what can x not be. Well, the only thing that x cannot be is -3. That means that x can be any other number in all of the reals. X can be any other real number. The only number that x cannot be is -3. So if we're going to write that in interval notation, x can be anything from -infinity up to -3, but not including -3. So here, see, we use a parenthesis that says up to, but not including -3. But then what we can do is we can skip over -3 and keep going to infinity. So this is the way you write the interval notation that says anything from -infinity to infinity except -3. And since there is a gap, you will need the union symbol. Remember, the U is the glue that sticks the two pieces together. Set notation interval notation. You can write it either way, but you need to be prepared for either one. And if I wanted to show this on Desmos real quick to give you a visual, here is our function. I'm going to go ahead and turn it on. And you can see that it's kind of a cool looking function. Notice the domain here. If I scroll back to the left, this graph is going to go forever to the left. And then notice as it comes up to -5, -4, -3, look what it's doing. It's heading down, and the x's are going to get closer and closer and closer to -3, but it's never going to touch at -3. But then on the other side of -3, look, it comes way up here, and it continues on to infinity. So what we call this on this particular graph, we call this number that the graph is approaching but never touching an asymptote. So here I'm showing x equal -3 is where the asymptote would be. And the definition there, an asymptote is a line that the graph approaches but never touches. No matter how high I go, if you see, I'm going to click on this graph, see it's at -2.95, and the higher I go, the closer it gets to -3, but it's never going to be -3. -3 is not included in the domain. And so there's a visual that shows exactly why -3 doesn't exist in the domain. It's because the graph does not exist there because of the restriction. And I think that's going to do it for number 9. All right, for this last example in this section, we're going to look at a square root function. There was not an example in the exercise set like this, so I made it up. This is my first example. And here we have h of x is the square root of 5x plus 15. You need to know that this is a square root function because we have a radical symbol with an index of 2. The index is the little number that sits right here on the radical. And if there is no number showing, that indicates a square root. So since the instructions say find the domain, we need to know if a square root function has a restriction. And it does. The restriction for a square root function says that the radicand must be greater than or equal to 0. And the radicand is the stuff under the radical. So what we need to do to find the domain is we first need to find the restriction, and then we'll know what values x can be. So we're going to set the radicand greater than or equal to 0, and then we need to solve for x. Moving the 15 over makes it -15. And then if I divide both sides by 5, we can see that x has to be greater than or equal to -3. This is the restriction. If you leave it like that, that is not the domain, it's the restriction. So in order to write the domain, the easiest thing to do first would be to write it in set notation. So the domain would be the set of all x such that, and then you simply write the restriction. X is greater than or equal to -3. And there's your domain in set notation. We're also going to express that in interval notation. That would be everything from -3, and we use a bracket because -3 is included, to infinity. If x is greater than or equal to -3, it has to be everything from -3 to infinity. And that is set notation and interval notation. And that answers the question they ask. Now, what I'd like to do is I'd like to go to Desmos and verify that. So if we go to Desmos, I've already got my function typed in, and I'm going to turn it on. You can see that the graph, as we go from left to right, the graph starts existing at -3. That's a point on the graph, so -3 is included. And if I drag that over, you can see that that graph is going to go forever to the right. It's just going to keep going and going and going. So x can be anything from -3 to infinity. That's the domain. And since we've got the graph pulled up, it's also super easy to do the range. Let's go ahead and talk about the range for a second. Remember, the range are the values that y can be, and the range has to go from low to high. So there's no graph down here. The graph starts existing on the x-axis, which is at a y-coordinate of 0 here. And again, if I drag that graph over, you're going to see that that graph continues to increase forever. It's just going to keep going up and up and up forever. So the range would be everything from 0 to infinity. So it's pretty easy to get the range there from the graph if you need it. And let's go ahead and make a note of that. So the range in set notation would be the set of all y such that y is greater than or equal to 0. Or in interval notation, that would be everything from 0 to infinity. Just in case you needed the range, there it is. And it is possible to find that algebraically as well without looking at the graph. Remember that a square root has to equal a positive number, or at least 0. There's no way that a square root can produce anything less than 0. So we know that this function is going to output values of y that have to be greater than or equal to 0. So you could reason that out mentally or algebraically there if you wanted to. But the graph helps verify the domain and range. And I think that's going to do it for this lesson. So if you have any questions or comments about anything I've done, feel free to leave those in the comment section below, or you can text me. And thanks for watching.